All right, guys, so any questions from homework first? All right. I'll continue being an optimistic fool and assume that means everything's going great with homework, that I'm not kidding. So I think everybody's got this handout now, is that right? This remarkable, colorful handout. It's got the feature, if you flip it, that's what we did last time together. We haven't quite looked at this one directly yet. You can see some of this hopefully looks a little familiar. So I want to kind of real quick review the disk method we talked about last time, and then get into the shells method. And then I got a little separate shells handout, and then we'll talk about this really colorful one that's basically just an overview of everything all at once. This is kind of cool. There are so many things that we construct that have this rotational symmetry, meaning if you chop it through its center at any angle, it looks the same. So that's basically a shape that's been rotated. This happens in so many places. We have these 360-degree rotational symmetry objects. So this is the calculus behind finding the volume of these things. And the work that we do for this can be extended to do other things. And the same way that area, if you have, for example, the plot of a energy over time, and if you find the area, that'll be the total amount of energy used over that time. So there could be physical meaning behind the integration that we do. So that also applies here. But the basic idea, whatever you're probably going to use it for, is, for example, if I rotate the sucker around the x-axis. I had to do this thing. Oh, it's not too bad for me. This is key. This is key. If I go out to some x value, that is where there's this circle, right? So how do I locate these circles along the axis that I rotated parallel to? Let me say this again. How did I locate that circle? Where's another circle located? At another what value? Another x value. So if I'm using disk method, I locate the thing, in this case the circle that I'm using, I locate it on an axis parallel to the one I'm rotating around. So that means that if I rotate around some axis parallel to the x-axis, of course also the x-axis itself, I'm going to have integral dx. I don't know if I made a big enough deal out of this. I made a semi-decently big deal out of it. But this is what gets you started. Is it integral dx or integral dy? Because then everything else comes off of that. So if I'm going from A to B, for example, so it would be A to B, that's what x does. Right? And then what's the area of the circle? Because if I add up all the areas of all the cross-sectional circles all the way through, I'm going to, of course, end up with the volume of the whole thing. Does that make physical sense? Yeah. It's almost scary how much sense that makes. Please. So what is the area of that circle? What's the radius of the circle? Any circle at any x value, what's the radius? F of x. It's related to the height of the rectangles we used, remember? So now we're using that same idea for a different kind of purpose. That's the radius of the circle that I'll create when I rotate. So that's the radius. And of course, so what's the area of the circle? It'll be pi radius squared. I like it. So if I add up all those circles together, Then, of course, I'll end up with the total volume. It's too nice to believe. All right, maybe. So that's the basic idea. So, for example, if I had, what you got, Jeff? Let's do. Can you sketch a rough graph of that? So the region bounded by those two things. The region bounded by the function and y equals 0. Y equals 0 is another name for... Y equals 0 is another name for...
F of x?
X-axis.
Yeah, x-axis.
Because that's on the x-axis, all the y's are 0. You haven't gone up or down any. So sketch a graph of that region. This region smoothed out, basically. So coming out of pre-cal, I know I keep marking on this, but you should have a long list of things you immediately look for to help you sketch a rough sketch. So somebody tell me something about this function here. That's right, it's not a single bola, it's a parabola. I just can't wait for some of you like, teachers call it a parabola. What else can you tell me? It's a parabola opening down with, what else can you tell me, more specific?
0 and 5.
0 and 5, I like it. And it opens down. Is it important to know how tall it is?
Yes.
Nope.
No.
You gotta love this. Look back here.
Oh, right.
I know what f of x is. And then I could square blah, blah, blah. Bless you. So it's not important. I could figure out, I know this vertex would be a 2.5 right in between. I could plug that in. Who gives a shit? So this is the rough sketch. It's just a rough sketch. That's all I need. So yeah, part of doing math well is understanding when you just need a rough sketch and when you need a much more detailed sketch. That is a part of knowing math. Here I just need a rough sketch. Something to kind of label. And you never have to graph anything 3D. So if I do rotate about, I didn't even say this, about the x-axis. It's going to be integral d what then, if I want to use disks? Dx, because I'm rotating around something parallel to the x-axis, namely the x-axis itself. If I rotated around the y-axis, it would have been integral dy. I like it. Shell method is going to be the exact opposite. Because wherever this guy, disks, has issues, shell method won't have those issues. So they complement each other. Some things you can do both ways. But whatever you can't do one way, you can do the other way. It's kind of nice. So I got my pi. That's just a constant. I pretty much always put it outside the interval so it doesn't mess me up. What am I going from to?
0 to 5.
0 to 5. Now if this was dy, what would I have to kind of be more careful about on my sketch? If it was dy, then I would have to know what? The height of it. I'd have to work that in. That would actually be pretty gross to do with disk method. Where am I at? Oh, and then inside goes what?
5x minus x quantity squared.
Yeah, because that's the radius. You pick some arbitrary x value and you say, that's the radius. Am I hugging the axis of rotation? Am I hugging it? Is this hugging the axis? Yes. If it was not, if this was the axis, then I have to add some extra stuff because I'm a little further away from the axis. So the radius is always measured related to the axis of rotation. And then, all right, finish that out real quick. Please don't end up with two terms inside. That will make me cry. Big tears. you able to print that out? So let's see, we get 25x squared minus 10x cubed, I think, plus x to the fourth. Does that look all right? And then you get, what do you get here? Integrate.
Let's see.
Integrate this. What did you guys do this weekend? Dude, God, yeah. Forgot who I was for a while. What's that? All right, I want you to help me right now. You guys, I love you guys. You're all like, okay, we'll do it. Say it. What, 25?
Oh.
There it is. 10x to the fourth over 4, sure. X to the fifth over 5, evaluated from 0 to 5. I got my 0 to 5. And then just throw, now this is the boring stuff. Just throw that shit in there, get a number. All the interesting stuff is done. I don't even care. You guys can throw that in and see what it is. Okay. Some people always take that wrong. You didn't care about me or math or nothing. I don't give a shit. Let's just throw in numbers in. Okay. So that's disk method. So if I want to use disk method, let's say I had a function that looked like this, and I want to rotate it. Let's say I have this, let's say, let me make this something real. Say I have this side of this circle, right? That side of the circle. And I want to rotate it around the y-axis. If I want to use disk method, what's the first thing I realize? It's the most important initial step that gets everything else. It tells you how to do your limits. It tells you how to do your function. Yeah, it's going to be dy. Because I'm rotating around parallel to the y-axis, namely the y-axis. So I know it's going to be integral dy. So inside, what's this got to be a function of? Freaking y, right? What is this? What are these? You can do it. What's the radius? What's the radius?
It's f of x. So
No. What's the radius? 3. So what's this? Negative 3. 3 away. And then what's this? 3 away. Whew.
Oh. Right.
Circles. Got to be some of the easiest shit, right? You just got to... Oh, it's a circle. Thank God. That's easy shit. Now what do I do with this so I can throw something in here? What do I do? Which means what? Solve for x. Because then it'll be x equals a function of y. I love it. That's why I ask a follow-up question. Really, you realize what you're saying. So if I solve this for x, why do I not put plus or minus? Why do I pick the plus?
Because there's nothing on the
Yeah, this is the positive x part of the circle. So I'm going to pick the positive x part of the freaking circle. And then I throw this shit in there. Weehaw! Now look at this one. I love this example. You might be as scared of the fact that it's a square root, because integrating square roots might get a little freaky, but what's the first thing that happens to it? The square root goes away. What are the limits? Yeah, because it's... Do you see? I really want you to understand. That's why this is almost the first step. Right after you sketch your graph, this is your immediate next step. It's integral d what? Because it tells you what the limits are related to, and it tells you what this has got to be a function of. So if it's disk method, when I'm rotating about whichever axis, it's d that. Rotate around the y-axis or something parallels dy, same thing around. Shell method, the exact opposite. So this goes from -3 to 3. Some of you guys might realize this is a symmetric region. If I went from 0 to 3, double it. Right? Does that make, do you guys see that?
Yeah.
You gotta be really careful about what's truly symmetric. If you want to do something like that, and if you just maybe just never do it, if you're like, okay, I'll never do it. And then you can finish that out. Right, this will square, this will be easy to integrate. Are you guys, is that cool? The integral step now, hopefully, will be the easy step. It's setting it up that gets a little freaky sometimes. Okay, so, with that in mind, here's my little, it was going to be in color, and then I didn't realize, my printer didn't warn me it was out of ink. So too bad for us. Try to do that first thing on there. See the reason I'm talking about, it says try discs. So try to set that up using discs. You know going in that something's going to go wrong.
Set up whatever it is.
So what am I rotating this around? Here's the region, by the way. Don't mess with this. But that's, I've sketched it for you down here. But what do you notice right away? I mean, even before you try to sketch it, I already gave you a sketch. What's the next thing after the sketch?
Function.
See again?
The function.
What about it? I mean, even before anything about the function. This is integral d what? It's disk method. I'm going around the y-axis. So it's integral d y. Guys, so again, unbelievably important is to remember that disk method is integral d blank, where the blank is the axis I'm rotating around, so that I'm parallel to. See, I'm rotating around the y-axis. Disk method requires dy. You guys see the problem that leads to? So I must have integral dy. So what must the inside be a function of?
Function of x. No. What?
Yeah, so it's integral dy. The function inside has to be a function of y. Is everybody cool with that? If I put a function of x in there with dy, you don't know what the shit to do yet. That's Calc 3. Calc 1 and 2 is single variable calculus. Calc 3 is multivariable. You want to do some Calc 3? No. Okay. What is it currently a function of? It's a function of x. Can you solve that for it to be a function of y? Some of you guys aren't sure at the moment. But you should be able to look at it and go, well, no, I can't get x by itself. I can't. There are some ways to do it that are remarkably disgusting. I would never want to deal with that integral. So this is motivation as to why disks alone isn't good enough. We stop here for a second. Do you remember what I said about this shell method? If disks are dy, shells will be dx. Do you see how that... Okay, if I have another method that allows me to be dx, wouldn't that be better? Because I got a function I can't solve for x. So I need a method that allows there to be a dx here. All right, so this is good motivation as to why there's a whole other method to do this shit with, because this method doesn't always work. So we need some other method to help fill in the blanks. So here's the other method. Give up on disks. For right now, for this problem. Don't give up on disks in general. So this is just a little example of a problem, and it's not our function. I needed something just to draw on separate from this. If I were to find the area of this region, I would just make a little rectangle here, right? And make a bunch of little rectangles, and the number of rectangles go to infinity and all that weird shit. You with me? Okay. That rectangle, what axis am I rotating around in this example? You guys see?
Yeah.
The y-axis. Okay. Do you remember how in the disk method, I locate my circles along the axis that I'm rotating around? So this will be a certain x value, will be that's where that circle is. And that's why, if I go around the x-axis, it's got to be integral dx. Look at this rectangle. What locates that rectangle? Where's there another rectangle at a different value of x? But what am I rotating around? Y. So the rectangles will always stand up parallel to the axis you're rotating around. They'll stand on the axis, the other axis, the one that's perpendicular. Right? So I'll locate this rectangle on the other axis, not the one I'm rotating around. That's what allows it to be, or actually makes it have to be dx if I'm rotating around y and vice versa. I love this idea of disks. I find the circles along the axis I'm rotating around. That's why they agree. Rotate around the x-axis, dx. Here, the rectangles, I locate them on the axis that's perpendicular to the one that I'm rotating around. That's why if I'm going around y, it's going to be integral dx. That's why they complement each other. When I have a function I can't solve for a certain variable, I can pick the method that will work with that. Does that make any sense? You're all like, do so much, man. Okay. So here's what the whole shape, this shape, if I rotate it, this is our little bundt cake pan. Remember we talked about the bundt cake pan? Did anybody look that up? You have no idea what that looks like. It basically looks like this. It's got a hole down the middle. You put it's basically upside down, put your cake batter in there. Yummy, yummy. Now watch this. Here's that little rectangle I drew. Here it is. And it's been rotated. I'm just going to draw half of it around. That's like a slice. That's like a slice of that shell. So there's a picture of a shell right here. So what we have to do, what was disks based on? Areas of circles. All right, formula for the area of a circle, easy as shit. I throw that in the integral, I'm good. These are based on volumes of cylindrical shells. Oh, shit. Okay, so let's remember what is the surface area of a cylinder. Oh, shit. Not including the top and bottom. Just the surface area. Yes, I like it. What'd you say? If you do what? Have you guys ever taken a soup can label off a soup can? So you chop, you slice that one side, you open it up, and it makes a rectangle, of course. If you take a rectangle and you fold it, you've made a cylindrical shell. You've all done this before, right? You fold a piece of paper up, hey, what's going on? And you just made a cylinder out of a rectangle, right? So if I chop this thing down the side, just chop. Well, real quick, somebody help me out. How far around is this? 60? How far around is that?
How long?
Circumference, sure. 2 pi, thank you. Okay. So I need a formula for it. And how tall is this? We'll call it h. I like it. So if I unfold this into a rectangle, so I just pick this up and put it down here, how long is this? It's 2 pi r. And it's still how tall? H. So what is the area of this? 2 pi RH. So for every x value, when I rotate it, it makes another shell. Now, just to complete this idea, I have a little thickness here, right? So it's more like, what's a good example? Jeez. Oh, come on, like a pipe that's got it's got a thickness to it, right? It's not just paper thin, because you want this sucker to hold up to whatever, so it's got a thickness to it. That's what makes it a volume I'm talking about. Well, how thick is that? What is that? What is that little arrow? How long is that? dx. I love it. So this is dx. So do you see how if I do 2 pi RH times dx, that is the volume of this shell. That is the volume of the shell. And how many shells do I have? Well, I have an infinite number of shells all the way along, right? For every value of x, it's another shell. Move a little bit. There's another shell. Move a little bit. There's another shell. So then if I just add up all of those shell volumes, I'm going to end up with the total volume of the shape. It's actually a really just beautiful idea. I remember when I first learned this shit, and that is so deceptive. That little line there, you never would realize it represents a three-dimensional object. So of course, what's the height going to be? The height's going to be what it almost always is. In this case, f of x. Whatever that function is. It could be a function of y if I'm rotating around the x-axis. Right? So let's try this one together. So the same way with disk method. Any method you're going to use, after you sketch the region, you want to know interval d what. I am rotating around the y-axis. Disk method would be dy. Therefore, shell method would be dx. Maybe that's how you can remember. Disk method is the one that goes right along. It's like, okay, cool. Y-axis, I'll make it dy. X-axis, I'll make it dx. Shell method is like, oh, there might be trouble. I'll do the other one. Right? So if you want to memorize this, you go, disk is always the same. Shell is the opposite. So disk would want dy. Shells want dx. Why is that good? Because my function is a function of x that I can't make a function of y. So I want integral dx. Here's my 2 pi. What am I going from to? Now I've got a sketch to look at. 0 to 2. So for some arbitrary value of x, there's my little rectangle. And when I rotate it, oh crap. Hey, look, it's Donald Trump. All right. So when I rotate this thing, I'm going to make a shell. So I need to know. Well, somebody help me out. What is this? That's my arbitrary x value, right? Well, what does that represent physically? What's that represent for that shell? That is the radius. Does everybody see that? That's the radius of the shell. So this will be 2 pi r, which in this case is x. Do you see that? The radius is x. And what's f of x? That's the height. What's the height? 2x squared minus x cubed. One kind of nice thing about this, which isn't always nice, because there was an example here where the square saved us, is there's no square there, you know? Kind of makes things a little grosser sometimes in the disk method. There's no square, but there is an extra x, so sometimes that can make things weird too. But this one's not bad. Go ahead and finish this one out. Okay. Notice something too. This method, the shell method, there's no washer method to this. There's no inner outer radius ever. If I were to try to do this with disk method, I actually have to do inner radius and outer radius. Because is it hugging the axis I'm rotating around? No. So another general better thing about shells is it's always the same. It's never like an inner outer radius or something. You know, it's not two different kind of things you do. It can handle empty space easily. Okay. So let's look at the really colorful sheet for a second. I pointed this out before. There's the disk method. So you locate the circle on the axis you're rotating around, which is why it's this D whatever that you're rotating around. There's the washer method, which is really the disk method. You just calculate two disks and take the difference. You're like chopping the middle out. So you subtract. I call it a cookie cutter problem. It's like a 3D cookie. And then here's that shells method with some better drawings, computer generated, will always leave me out. So it's always 2 pi radius times height times thickness. So you got to be a little careful. So see here, here's an example. I've got this upside down parabola that I'm rotating around the y-axis. This is what that looks like. This always looks like cheese to me. No, big thing of cheese. But this is what it kind of looks like in the end. See how this isn't really, this is like a finite number of rectangles. So it's a very low resolution there. But that's capturing the idea of what we're doing. If I were rotating not around the y-axis, let's say I was rotating around x equals -1. What would the radius be then? The radius is always the distance from the axis of rotation out to the thing you're rotating. So what would that radius be now?
X plus 1.
X plus 1, that's it. Right? So if you just draw the picture, you don't have to do any of the 3D shit that's on there at all. Just draw the picture, put the axis in, just go. Just draw a line over to just an arbitrary rectangle. And just, how long is that? That's all you're doing. That's the radius. Okay, so let's do this. Going to need some more room for this. So if you read through there, this captures a lot of what I've been talking about the whole time. You locate, the disks are located along the axis they revolve around. Shell method, the rectangle is located in axis perpendicular. That's why one is dx while the other is 2y. And then I give you a little bit of the same stuff we were talking about earlier. So I want you to try to do this problem. I've given you the region here. I want you to do it both ways. Try to do this problem both ways. I'm not saying it's going to be like quick and easy, but it's not going to be crazy hard either. Please maybe consult with somebody else at some point if you want to. Or let me know if you need some help. Oh yeah, sure. Maybe else need a copy of that? On the other side is this guy, yeah.
So which one are we going for? We just need 5 wires in the middle of that, right?
Which axis are you rotating around? Y-axis. So which method would allow you to do dx? The rotator on the y-axis, which method lets you use dx? Shells. Well, that might be why it's a place to start, but maybe you're going to run into an issue. Let's find out.
There's two.